in this video, I'm going to be talking about Fischer esterification. So what does Fischer esterification do? Well, it's going to take a carboxylic acid and turn it into an ester. So let's do a quick review. A carboxylic acid has an OH side chain and an ester has an OR side chain. That R is a carbon chain, and that carbon chain can be 1 carbon long or it could be 100 carbons long, still counts as an R group. The next thing we want to consider is in what conditions does Fischer esterification occur. So those conditions are typically acidic, and acids usually diluted with water, so you're going to end up having some water in solution, and an alcohol group. That alcohol group is characterized by that OH and, of course, the R group, which can be, again, any carbon chain that's 1 carbon long. It could be 100 carbons long, doesn't really matter. So let's move straight into this reaction. So you're going to start out with a carboxylic acid, and it's going to react with acid. That oxygen is going to grab a proton and become positively charged because it has 3 bonds and 1 lone pair. And this next part is really special for Fischer esterification because it's going to form a resonance structure where the double bond breaks and returns as a lone pair to that oxygen. And you're going to have a positive charge at this carbon because this carbon had 4 bonds, but this carbon only has 3 bonds. And it's going to use this minor product, which I'll write down here, to perform the next part of this reaction. This next part of the reaction is going to react with the alcohol group, and the lone pair on that oxygen is going to attack that carbon and attach there. So let's keep in mind that the oxygen is what is attacking, so the oxygen is what is attaching to that carbon. So you're going to have this alcohol group attached via the oxygen to that carbon. And of course, this is going to be positively charged. We want to make this alcohol group uncharged, so a base is going to deprotonate that hydrogen, and the electrons that were holding hydrogen in place are going to return to that oxygen so that that oxygen has 2 lone pairs. So let me go ahead and redraw that. So you have an OH here and an OR with both its lone pairs, and again, that hydrogen was removed, so it's no longer attached here. We formed an acetyl here, but that's not our goal, right? Our goal is to form an ester, which has that characteristic carbonyl bond, so we want to go ahead and reform that. So in order to do that, we need to react with acid once again, and that acid is going to donate a proton to one of these oxygens. So oxygen is going to grab a proton and form OH2, which is also known as H2O, which is water. And we know that water prefers to leave, it doesn't want to stay attached. So in order to do that, one of these oxygens, or I'm sorry, not one, this oxygen, which is attached to the H, is going to take one of its lone pairs and reform that double bond. And again, you can't have 5 bonds to a carbon, so this water is going to go ahead and leave. And we're going to form something like this. This carbon group has been here this entire time, it's right here. And this OR group is what we've worked so hard to attach. And of course, this double bond is what we just reformed, moving this lone pair down. Proper workup says that this hydrogen is going to get deprotonated by some type of base, and you're going to end up with an OR group. And there's our ester.